Hello everyone. Let's begin today's session with a thought. Have you noticed how a car steadily picking up speed from a traffic signal feels smooth and predictable? That's an example of uniform acceleration. In physics, acceleration means the rate of change of velocity with time. When this acceleration remains constant, we call it uniform acceleration. Classic examples are a ball falling freely under gravity if we neglect air resistance, or a train gaining speed smoothly. In such cases, we need equations that connect displacement, velocity, acceleration, and time. These are what we call the equations of motion. And believe me, they form the backbone of solving most real-life motion problems. Let's derive the very first equation of motion step by step. Suppose an object starts with an initial velocity, u, and after a time t, its final velocity becomes v. If the acceleration is constant and equal to a, then by definition, acceleration equals open bracket final velocity minus initial velocity close bracket divided by time. So, a equals open bracket v minus u close bracket divided by t. Rearranging, we get v equals u plus a t. This simple yet powerful equation tells us that the final velocity is the initial velocity plus the product of acceleration and time. For example, if a car begins at 10 meters per second and accelerates at 2 meters per second squared for 5 seconds, the final velocity becomes 20 meters per second. Now, let us move to the second equation of motion, which gives displacement. Displacement, s, is simply distance traveled in time t. Average velocity under uniform acceleration is open bracket initial velocity plus final velocity close bracket divided by 2. Substituting v equals u plus a t, we get average velocity equals u plus half a t. Therefore, displacement s equals average velocity multiplied by time, which becomes ut plus half a t squared. So the second equation of motion is s equals ut plus 1 by 2 a t squared. This beautifully relates displacement with time when acceleration is constant. Time for the third equation of motion. We know displacement s equals open bracket v plus u close bracket divided by 2 into t. From the first equation, t equals open bracket v minus u close bracket divided by a. Substituting this, we get s equals open bracket v plus u close bracket by 2 multiplied by open bracket v minus u close bracket divided by a. On simplifying, 2as equals v squared minus u squared. Hence, v squared equals u squared plus 2as. This third equation directly links velocity, displacement, and acceleration without involving time. Another way to understand these equations is through a velocity-time graph. Picture a straight line graph where velocity increases uniformly with time. The slope of the line gives acceleration. A equals open bracket v minus u close bracket divided by t. And the area under the velocity-time graph represents displacement. Here, displacement equals the sum of the rectangular area under u and the triangular area under acceleration. That gives s equals ut plus half a t squared. As you can see in the diagram, the rectangle plus triangle areas beautifully explain the second equation. Let's test our understanding with a problem. Suppose a body starts with an initial velocity of 5 meters per second and accelerates uniformly at 2 meters per second squared. Find its displacement and velocity after 10 seconds. Step 1. Apply the first equation. V equals u plus a, t, which is 5 plus 2 into 10, giving 25 meters per second. Step 2. Apply the second equation. S equals ut plus half a t squared. That is 5 into 10 plus half into 2 into 100, which equals 50 plus 100, giving 150 meters. So in 10 seconds, the body covers 150 meters and reaches a speed of 25 meters per second. A similar calculation is done in railway engineering when estimating how far a train travels as it steadily picks up speed. Let's quickly revise the three equations of uniformly accelerated motion. First equation, v equals u plus a t. velocity and time relation. Second equation, s equals ut plus half a t squared, displacement and time relation. Third equation, v squared equals u squared plus 2, a s, velocity and displacement relation. These equations describe motion in one dimension under constant acceleration. Their applications are endless, from free fall to rockets, from speeding vehicles to planetary motion. So, to sum up, equations of motion aren't just textbook formulas. They are tools to understand how objects around us move in the real world. I hope this session gave you clarity on the topic. See you in the next class with another exciting concept of physics.